Welcome to the nucleus, isotopes, and atomic mass. So we've already discussed a little bit about atomic structure in the last video, and now we're going to go into it in a little bit more depth. So the nucleus lies at the center of the atom, and it contains our protons and our neutrons. Remember that outside the nucleus we have our electrons in the electron cloud or in the orbitals. This means that the nucleus contains nearly all of the mass of the atom because the electrons have a negligible mass in comparison to the protons and the neutrons. Furthermore, the nucleus is very, very tiny compared to the size of the atom, which is itself very, very small. But if almost all of the mass of the atom is contained in the nucleus, but the nucleus is very, very tiny in relation to the atom, that means that the nucleus itself must be really, really dense. And it turns out that nuclei are so incredibly dense that they're denser than anything else that we have any experience with in our daily lives. They're far denser than anything else on the Earth's surface. So, because the nucleus contains all the protons and it contains no electrons, that means that the nucleus is positively charged, regardless of how many neutrons it contains. But also, there are no positive charges in the atom outside of the nucleus. So, all of the positive charges are in the nucleus, all of the negative charges are outside the nucleus, all of the neutrons, which have a zero charge, are in the nucleus as well. Let's talk about types of nuclei. There are only certain combinations of protons and neutrons that will form a stable nucleus. In a nuclear reaction, this is a reaction in which the nucleus is changed. If an unstable nucleus is formed, it will decay relatively shortly thereafter. And there are three types of nuclei. There are stable nuclei, radioactive nuclei, and unstable nuclei. Let's talk about stable nuclei first. Stable nuclei do not change outside of a nuclear reactor or a star over billions and billions of years, which means that if you're looking at a stable nucleus that is on Earth, like in the oxygen that you're breathing right now, those oxygen atoms have been around, those nuclei have been around for billions of years, basically since the Earth formed, and in fact before the Earth formed they were floating out in space somewhere, and before that they were made in the heart of a star, and that subsequently exploded and spewed its guts out into the universe. So those nuclei haven't changed in billions and billions of years, and that is how stable most of the nuclei on Earth are. Then there are radioactive nuclei. Radioactive nuclei are semi-stable, they're just kind of stable. Once formed, they can last for a time before they fall apart. This is called a process called decay, or radioactive decay. So radioactive nuclei decay at some predictable rate characteristic of that particular nucleus. They may last from anywhere from a few seconds to a few billion years. So even some of the atoms or some of the nuclei on Earth's surface are radioactive, but they've been on Earth's surface for a very long time. So these are things like uranium and plutonium that we use in our nuclear reactors to generate electricity for powering light bulbs and computers and things like that. And then there are unstable nuclei. So unstable nuclei decay within just a few seconds and often in just very, very small fractions of a second. And so generally these are formed in some nuclear reaction. They are so unstable that they decay relatively quickly. They're still radioactive, but they just decay so quickly that essentially on Earth's surface there aren't any of these, at least outside of material that has recently been created in a nuclear reactor. So Earth's crust contains all of the stable nuclei and some of the radioactive nuclei, but naturally we don't find the unstable nuclei on Earth because they would have decayed within a few seconds of forming within a star. They basically wouldn't have even made it to Earth's surface in the first place. Every once in a while, one of the radioactive nuclei will decay, generating an unstable nucleus, and then that decays within just seconds after that. So for all elements up to 82 protons, this is lead. Lead has 82 protons. For all elements up to 82 protons except technetium, which has 43 protons, and promethium, which has 61 protons, at least one stable nucleus exists, which means that we see all of those on Earth's surface. Because they're stable, they'll stick around for billions of years, and that means that they can accumulate on the Earth. Atoms with 83 to 92 protons are all found on Earth, but they're all radioactive, which means that they all decay. These are generally things that are pretty dangerous to have around, because the radioactive decay process can let off lots of energy and lots of radioactive particles that do bad things to human tissue. Atoms with 93 or more protons only exist on Earth when they're formed in nuclear reactors or nuclear reactions as occur in nuclear reactors. Now, over 99.99% of Earth's atoms contain stable nuclei, and just a really tiny fraction of atoms are radioactive, which means that the vast majority of atoms on Earth haven't changed since the planet formed billions of years ago. Or rather, the vast majority of nuclei on Earth. The atoms themselves may have changed. They may have gained or lost electrons many, many times over the years, but the nuclei themselves haven't changed. So let's look at some more terminology. Protons and neutrons are called nucleons because they're in the nucleus. So electrons are not nucleons because they don't reside in the nucleus. A combination of protons and neutrons is called a nuclide. That is, a nuclide is a type of nucleus of one particular element. So, some combination of protons and neutrons. Atoms of the same element, as the same number of protons, can have different numbers of neutrons. And each combination of protons and neutrons for a particular element is called an isotope of that element. For example, all atoms with 17 protons are called chlorine atoms. And there are only two chlorine nuclei that are stable, one with 17 protons and 18 neutrons, and the other with 17 protons and 20 neutrons. Any other number of neutrons with 17 protons is unstable and decays within just a few seconds. Each nuclide is assigned a mass number that is the sum of the number of protons and neutrons in the nucleus, and the mass number is the number of protons, P+, plus the number of neutrons, N0, so that's the number of protons plus the number of neutrons. When we add those together, that gives us the mass number. For example, a nucleus with 2 protons and 2 neutrons is helium. Because it has 2 protons, it must be helium. And if it has 2 neutrons as well, then it has a mass number of 4, because 2 plus 2 is 4. If we go back and we look at this case, where we had 17 protons and 18 neutrons, there we have a mass number of 35, because 17 plus 18 is 35. If we have 17 protons and 20 neutrons, we have a chlorine atom with a mass number of 37. So we can identify a nuclide in 3 different ways. The number of protons and the number of neutrons, using the Nuclide symbol, also called the isotope symbol. So this is the element symbol for the plus the mass number superscripted in front, so that's on the top left corner of the element symbol. Or we could describe it using the name of the element plus the mass number, and generally we put a hyphen in between. So for one isotope of chlorine, we can refer to it as 17 protons and 18 neutrons. Or we could refer to it as this way, with a 35 superscripted before the Cl for chlorine. Or we could refer to it this way as chlorine-35. Note that for both of these cases, we read it as chlorine-35, so we speak it out loud the same way. And the 35 is again coming from the 17 protons plus the 18 neutrons. 17 plus 18 is 35. We can refer to our second type of chlorine, or second isotope of chlorine, as 17 protons and 20 neutrons, or as chlorine-37, or chlorine-37 written this way as well. And given any of the 3 representations of the nuclide, you should be able to write the other 2. Because again, if we have, say, this symbol, a Cl with a 37 superscripted, we know that from the Cl that we have 17 protons, because we look at a periodic table and we see that chlorine's atomic number is 17. And then 37 minus 17 gives us 20. That means that we have 20 neutrons and 17 protons. So we can write this, and given this, we can write that as well. Note that sometimes the nuclide symbol includes the charge of the nucleus, subscripted in front. So A there, here, that is the mass number. So for our chlorine-35 example, A is 35. The Z here is the atomic number of our element. So this is the number of protons. So for chlorine, that number is 17, regardless of what the mass number is. X there is the element symbol, which in the case of chlorine is the capital C, lowercase l. And this is also sometimes called AZ notation. Now, we can measure the mass of a single nuclide in atomic mass units, or AMU. Protons have a mass of 1 AMU, neutrons have a mass of 1 AMU, and electrons have a mass of 0.00055 AMU. This is about 1/1800th of the mass of a proton, so we generally ignore the mass of the electron. And you might expect that the mass of a chlorine-35 atom to be just over 35.0 AMU, because the sum of the masses of 17 protons at 1 atomic mass unit apiece, plus 18 neutrons at 1 atomic mass unit apiece should give us 35, plus 17 electrons at just a tiny fraction, that should give us something just over 35. But in reality, the mass of that atom would be 34.97 AMU. Which is strange, because this is in fact less than the 35.0 AMU that we expected, not more. Why? Why is that mass less? It turns out that when protons and neutrons combine to form a nucleus, a huge amount of energy is released. This is why nuclear reactors are so much more powerful than burning fossil fuels for the same mass of fuel. So mass and energy are related by Einstein's famous equation, E equals mc squared, where E here is the energy gained or lost, m is the mass gained or lost, and c is the speed of light in a vacuum. Well, if nuclear reactions are giving off a huge amount of energy, that means that energy is being lost by the atom. If energy is lost by the atom, Einstein's equation says that mass must be lost by the atom. So when we have these protons and neutrons combine to form a larger nucleus, some energy is given off. That means some mass must be lost. And some mass is leaving the atom in the form of energy. So release of a large amount of energy results then in the loss of a very small amount of mass. And this means that the combination of protons and neutrons, the nucleus, has a smaller mass than the protons and neutrons by themselves. It's not a whole lot, but it's there, and we can measure it. This means that the mass of a nuclide will be very close to, but not exactly equal to, its mass number. Now, for most first-year chemistry classes, you can approximate the mass of a nuclide as its mass number. These small differences for loss of that energy will be small enough that in most first-year chemistry courses, you shouldn't have a problem. For most elements on Earth, samples of that element will contain a few different isotopes in some ratio characteristic of that element, and perhaps characteristic of where on Earth you found that sample of the element. Now, because the ratio is virtually the same in every sample of that element on Earth, again, there are a few cases where the ratio changes. We can calculate an average mass of the atoms of that element. And this average is what we call the atomic mass of that element. And this is a weighted average of the mass of its isotopes. That is, the mass of each isotope is weighted by the fraction of atoms of that element that are that isotope. So the atomic mass is equal to the fraction that is isotope 1 times the mass of isotope 1 plus the fraction that is isotope 2 times the mass of isotope 2, and so on for all the isotopes that we see. And remember, the fraction of something is equal to the percentage of that thing divided by 100%, which means that each fraction is somewhere between 0 and 1. And just like the sum of all percentages must equal 100%, if we divide 100% by 100%, we get 1. So the sum of all fractions must equal 1. For example, in samples of chlorine, 75.8% of the atoms have a mass of 35.0 AMU. Now, you and I know that that's not really 35.0. We know that it's really 34.97, but we're going to round for this case. And 24.2% of the atoms of chlorine have a mass of 37.0 AMU. And suppose we want to calculate the atomic mass of chlorine. Well, we know the atomic mass is equal to the fraction that is the first isotope, so 0.758 times the mass of that first isotope, 35 AMU, plus the fraction of atoms that are the second isotope, 24.2%, so 0.242 times the mass of that second isotope, 37 AMU. And when we carry out the math, we get 35.5 AMU. Now, note here that there is not a single atom of chlorine that has a mass of 35.5 AMU. They all have either a mass of 35 or they have a mass of 37. None of them have a mass anywhere in between. But the average over a large sample of chlorine, by which here we mean a sample that we can see with our unaided eyes, the average mass of all the atoms will be 35.5 AMU. So just like if we take a number of people within a room and we average all of their heights, we won't have exactly the same height for everybody. We'll have some range of heights, but when we average them together, we'll get some number. Now, there may not be anybody that has that height. In this case, we basically have two different heights of people. We have some short people, some tall people, and nobody in between. And it's not possible to be in between. That is essentially what's going on here. So the average mass is a weighted average of the masses of the individual isotopes. Now, chlorine is a relatively simple one because it only has two isotopes that have any abundance, but there are some other elements that have 3, 4, 5, 6 isotopes that have a measurable abundance to them. And so the calculation gets somewhat more complex. Now, chemical reactions can release a good deal of energy, as seen in the burning of fossil fuels and conventional explosives like TNT, trinitrotoluene, C4, plastic explosives, and so on. But nuclear reactions release far more energy, as seen in stars and nuclear explosions. In chemical reactions, atoms are not created or destroyed, they're just rearranged. We just rearrange the bonds between atoms. But in nuclear reactions, atoms are often created or destroyed, nuclei are changed, and this involves huge amounts of energy. Because chemical reactions and nuclear reactions are so different, we have to be careful with the terms chemistry and nuclear chemistry. Chemistry refers just to chemical reactions and not nuclear reactions, while nuclear chemistry refers to nuclear reactions. So in chemistry, nuclei of atoms are not changed at all. In nuclear chemistry, the nuclei of atoms are changed. So if you hear someone speaking of chemistry, we generally are not including nuclear chemistry in this. And so for the remainder of the course, the term chemistry does not include nuclear chemistry, and that means that nuclei of atoms are not being changed. Because chemistry does not involve changing the nuclei of atoms, we can generally ignore the fact that different atoms of the same element may be different isotopes, and we can simply assume that they have the average atomic mass of that element, even though we know that that's not really true. That is, when doing a calculation, use the atomic mass listed on the periodic table. Remember that that mass listed is an average, it's a weighted average for the mass of each atom of that element, because as long as we're using a large number of atoms, then this will work out fine. We can't use this assumption when we're discussing nuclear chemistry, including radioactive decay, fission, and fusion, because in this case, we're actually looking at individual atoms, and they're going to act differently depending on what their atomic mass is. But in chemical reactions, they act almost the same. So that was the nucleus, isotopes, and atomic mass.